Right now, you are moving, not walking, not driving. You are being carried through space at roughly 630 kilometers per second relative to the cosmic microwave background, the faint afterglow of the Big Bang itself. Your planet orbits a star at about 30 kilometers per second. That star orbits the center of a galaxy at approximately 220 kilometers per second. That galaxy is falling toward a gravitational anomaly 400 million light-years away, whose nature we still do not fully understand. And all of this is happening inside an expanding universe where the space between galaxy clusters is growing faster with every passing moment. None of this is perceptible. The ground feels still. The sky looks calm. That disconnect between what we experience and what is actually happening is the central problem with understanding cosmic distances. The numbers are available. They have been measured with extraordinary precision. But the human brain evolved to navigate landscapes measured in meters, to judge threats at distances of a few hundred paces, to plan journeys across tens of kilometers at most. Asking that brain to comprehend a void 300 million light-years across is asking it to do something it was never built to do. And yet, the distances are real. Their consequences shape the fate of every galaxy, every star, every civilization that could ever arise in the universe. Understanding what those distances actually mean is not a matter of awe. It is a matter of physics. Start with something close. The moon is the nearest celestial body to Earth, hovering at an average distance of about 384,400 kilometers. Light covers that gap in roughly 1.3 seconds. It is close enough that humans have physically visited it, walked on its surface, and returned home. The Apollo missions of the 1960s and 70s accomplished this with computers less powerful than the device in your pocket. The moon is, in cosmic terms, practically touching us. Now consider the sun. It sits about 150 million kilometers away, a distance so standard that astronomers use it as a unit of measurement called the astronomical unit. Light from the sun takes approximately 8 minutes and 20 seconds to reach the Earth. If the sun vanished at this exact moment, you would not know for over 8 minutes. You would continue to feel its warmth and see its light for those final minutes, while the gravitational signal of its disappearance propagated outward at the speed of light. This already introduces an uncomfortable truth. We do not experience the universe in real time. We experience it on a delay proportional to distance. The further away something is, the older our information about it. At the moon's distance, the delay is negligible. At the sun's distance, it is significant enough to matter in principle, but not in practice. Beyond that, the delays become enormous. Mars, when it is closest to Earth, sits roughly 55 million kilometers away. A radio signal takes between 3 and 22 minutes to travel between Earth and Mars, depending on orbital positions. This means that any rover operating on Mars cannot be directly controlled. Commands are sent and received with a built-in delay. The rover must make some decisions autonomously, because by the time a human sees a problem on the screen, the problem occurred minutes ago. This is still inside our solar system. These are our neighbors. Jupiter orbits at an average distance of about 778 million kilometers from the Sun. Light takes approximately 43 minutes to reach it from the Sun. Saturn, the farthest planet visible to the naked eye from Earth, orbits at about 1.4 billion kilometers from the Sun. Its light travel time is roughly 1 hour and 20 minutes. Neptune, the outermost recognized planet, sits at roughly 4.5 billion kilometers from the Sun. Light takes about 4 hours to reach it. And Pluto, which orbits even further out at an average distance of roughly 5.9 billion kilometers, requires light more than 5 hours to reach. The New Horizons spacecraft, the fastest probe ever launched from Earth when it departed in 2006, traveled at approximately 58,000 kilometers per hour. Even at that speed, it took 9.5 years to reach Pluto. It arrived in July of 2015, performed a flyby lasting just hours, collected as much data as its instruments could gather, and then continued into the outer solar system. There was no slowing down, no orbiting. The energy required to decelerate would have been prohibitive. The probe screamed past Pluto and kept going, and Pluto is not the boundary of the solar system, not even close. Beyond the Kuiper Belt, the region of icy bodies where Pluto resides, lies a vast spherical shell of cometary material called the Oort cloud. No spacecraft has ever reached it. No telescope has ever directly imaged it. We infer its existence from the orbits of long-period comets. Comets that take thousands or millions of years to complete a single orbit and arrive from directions that suggest a spherical source region rather than a flat disk. The inner edge of the Oort cloud is estimated to begin at roughly 2,000 astronomical units from the Sun. Its outer edge may extend to 100,000 astronomical units, which is approximately 1.6 light-year. At that distance, the Sun would appear as just another star, barely distinguishable from the background of the Milky Way. Voyager 1, the most distant human-made object, launched in 1977, is currently about 163 astronomical units from the Sun. It crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, in 2012, but reaching the inner edge of the Oort cloud at its current speed would take roughly 300 years. Crossing the entire Oort cloud would take approximately 30,000 years. We have sent an object further from Earth than anything in human history, and it has not yet reached the front porch of our own solar system. This is the first lesson in cosmic distance. The solar system alone, our immediate cosmic neighborhood, is so large that crossing it with our fastest technology would take tens of thousands of years. Everything beyond it is measured in units that make these numbers look trivial. A light-year is the distance that light travels in 1 year in a vacuum. That distance is approximately 9.46 trillion kilometers, 9,460,000,000,000 kilometers. Written out, it is a number so long that the digits themselves convey no intuitive meaning. The light year exists as a unit precisely because kilometers fail at interstellar scales. The nearest star system to our Sun is Alpha Centauri, a triple star system located approximately 4.37 light-years away. The closest individual star in that system is Proxima Centauri, a red dwarf orbiting the pair of Alpha Centauri A and Alpha Centauri B at a vast distance. Proxima sits about 4.24 light-years from the Sun, which translates to roughly 40 trillion kilometers at the speed of New Horizons. Reaching Proxima Centauri would take approximately 73,000 years. The entirety of recorded human civilization spans roughly 5,000 years. We would need to sustain a mission for over 14 times the duration of all written history to reach the nearest star. Proxima Centauri hosts at least one confirmed planet, Proxima Centauri b, which orbits within the habitable zone where liquid water could theoretically exist on a rocky surface. The discovery was announced in 2016 using the radial velocity method, detecting the tiny wobble that the planet's gravity induces in the star. A second planet, Proxima Centauri c, was proposed based on additional data, though its confirmation has been debated. Whether Proxima b could support life is deeply uncertain. Proxima Centauri is a red dwarf, a small, cool star that emits powerful flares. These flares release bursts of ultraviolet and X-ray radiation intense, enough to strip the atmosphere from a close-orbiting planet. Because the habitable zone of a red dwarf is much closer to the star than Earth's distance from the Sun, Proxima b orbits so near to its star that it is probably tidally locked, meaning the same hemisphere always faces the star while the other side faces perpetual darkness. Whether such a world could sustain an atmosphere, maintain liquid water, or develop any form of biology is a question that current technology cannot answer from over 4 light-years away, and this is the closest star, the nearest possible target for interstellar exploration. If it is this difficult to reach, what lies beyond it is functionally inaccessible with any technology that exists or is currently under development. The stellar neighborhood, within about 20 light-years of the Sun, contains roughly 130 known star systems. Most of these are red dwarfs, small and dim, invisible to the naked eye. A handful are larger, brighter stars that have been known to humanity for centuries, like Sirius, the brightest star in the night sky, which sits about 8.6 light-years away. Sirius is a binary system. The main star, Sirius A, is roughly twice as massive as the Sun and about 25 times more luminous. Its companion, Sirius B, is a white dwarf, the remnant core of a star that exhausted its nuclear fuel and collapsed. Beyond this immediate stellar neighborhood, the stars of the Milky Way stretch outward in a disk, approximately 100,000 to 200,000 light-years in diameter. Our Sun sits about 26,000 light-years from the galactic center, roughly halfway between the core and the edge of the disk, in a region called the Orion Arm, a minor spur between two of the galaxy's major spiral arms. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in that number is itself staggering. We are uncertain by a factor of 4 about how many stars exist in our own galaxy. The reason is that most stars are small, dim red dwarfs that are difficult to detect across large distances. The bright stars that dominate the visible sky are a tiny minority. The rare, massive ones that burn hot and die young, despite containing hundreds of billions of stars. The Milky Way is overwhelmingly empty space. The average distance between neighboring stars in the Sun's region of the galaxy is roughly 4 to 5 light-years. In the denser regions near the galactic center, Stars are packed more closely, perhaps a few tenths of a light-year apart in the densest clusters. But even there, the space between stars is vast compared to the stars themselves. If you scaled the sun down to the size of a grain of sand, the nearest star would be another grain of sand, about 6 kilometers away. The galaxy would be a collection of sand grains, separated by kilometers, spanning a disk roughly 100,000 kilometers across. This emptiness has consequences that are not immediately obvious. When galaxies collide, which they do, the stars within them almost never physically strike each other. The Milky Way and the Andromeda Galaxy are on a collision course, approaching each other at approximately 110 kilometers per second. In roughly 4 to 5 billion years, they will merge. Computer simulations of this event show the two galaxies distorting each other's shapes, flinging stars into new orbits, triggering bursts of star formation as gas clouds compress, and eventually settling into a single large elliptical galaxy, sometimes informally called Milkomeda. But during this collision, the probability of any two stars directly hitting each other is negligibly small. The stars are simply too far apart relative to their sizes. A galactic collision is more like two swarms of bees passing through each other than two solid objects crashing. The gravitational effects are dramatic. Stars change orbits. Some are flung out of the merged galaxy entirely, becoming intergalactic vagabonds. But direct stellar collisions are essentially non-existent. The Milky Way is not alone. It is part of a small collection of galaxies called the Local Group, which contains roughly 50 to 80 galaxies within a volume about 10 million light-years in diameter. The two largest members are the Milky Way and Andromeda. The third largest is the Triangulum Galaxy, about 3 million light-years away, which is much smaller and may itself be gravitationally bound to Andromeda. The remaining members of the Local Group are mostly dwarf galaxies, small and faint collections of stars orbiting the two dominant spirals. The Large Magellanic Cloud and the Small Magellanic Cloud, visible from the southern hemisphere, are satellite galaxies of the Milky Way, located about 160,000 and 200,000 light-years away, respectively. Beyond the Local Group, the nearest large galaxy cluster is the Virgo cluster, located roughly 54 million light-years from Earth. The Virgo cluster contains over 1,000 galaxies and dominates the gravitational landscape of the local universe. Its central galaxy, Messier 87, is a giant elliptical galaxy, famous for hosting the first black hole ever directly imaged by the Event Horizon Telescope in 2019. That black hole has a mass of approximately 6.5 billion times the mass of the Sun. The space between the Local Group and the Virgo cluster is not truly empty, but it is as close to empty as anything accessible to observation. The density of intergalactic space is approximately 1 atom per cubic meter. For comparison, the air you are breathing contains roughly 25 quintillion molecules per cubic centimeter, which is 25 followed by 18 zeros per cubic centimeter. Intergalactic space is a vacuum so thorough that the best vacuum chambers on Earth cannot replicate it. The most advanced laboratory vacuums still contain thousands of molecules per cubic centimeter. Intergalactic space is emptier by a factor of trillions. In that near-perfect vacuum, there is no sound. Sound requires a medium to propagate, molecules that can compress and expand to transmit pressure waves. In intergalactic space, the molecules are so sparse that no pressure wave can form. If you were placed in intergalactic space without a suit, you would not hear your own scream. The air in your lungs would expand and escape. The water in your tissues would begin to boil in the near-zero pressure. Not because of heat, but because the boiling point of water decreases as pressure drops. You would lose consciousness within about 15 seconds as the oxygen left your bloodstream. Death would follow within 1 to 2 minutes, not from cold, which takes much longer, but from the simple absence of pressure and breathable atmosphere. And you would be surrounded by essentially nothing for millions of light years in every direction. No star close enough to see clearly, no planet, no structure, just the faint, uniform glow of the cosmic microwave background and the unimaginably distant smudges of galaxies far beyond reach. This is the reality of most of the universe. The bright, dense, structured parts, the galaxies and clusters and filaments, are a thin minority. Most of the volume of the universe is void. When astronomers zoom out to the largest scales observable, the distribution of galaxies reveals a structure that looks like a three-dimensional web or foam. Galaxies are not scattered randomly. They congregate along filaments, long thread-like structures that can stretch hundreds of millions of light-years. Where filaments intersect, galaxy clusters and superclusters form dense nodes, and between the filaments lie enormous regions of nearly empty space called cosmic voids. This cosmic web was first suggested by early galaxy surveys in the 1970s and 80s. The Center for Astrophysics Redshift Survey, conducted by Margaret Geller, John Huckra, and their collaborators in the 1980s, produced one of the first maps of the three-dimensional positions of galaxies in a large volume of space. The result was striking. Galaxies were not uniformly distributed. They formed walls and filaments surrounding enormous bubbles of empty space. The famous Great Wall, a sheet-like concentration of galaxies identified in that survey, stretches roughly 500 million light-years in length. Subsequent surveys expanded this picture enormously. The Sloan Digital Sky Survey, which began observations in 2000, mapped the positions of millions of galaxies across a quarter of the sky and confirmed the cosmic web structure at ever larger scales. The 2-degree field galaxy redshift survey performed similar work from the southern hemisphere. Together, these surveys revealed a universe that looks, at the largest accessible scales, like a sponge. Dense regions connected by surrounding vast empty voids. The voids are not perfectly empty. They contain a sparse scattering of galaxies, called void galaxies, that have evolved in relative isolation. These galaxies tend to be smaller, bluer, and more actively forming stars than galaxies in denser environments. Their isolation means fewer gravitational interactions, fewer mergers, and less of the environmental processing that strips gas from galaxies in clusters. The Boats void, discovered in 1981 by Robert Kirshner, Augustus Omler, Paul Schechter, and Stephen was one of the first voids large enough to attract widespread attention. It spans approximately 330 million light-years in diameter. Inside it, astronomers found only about 60 galaxies where, based on average cosmic density, they expected to find thousands. The discovery challenged existing models of structure, formation, and prompted new theoretical work on how voids form and evolve. Voids form through a process driven by gravity and cosmic expansion. In the very early universe, the distribution of matter was nearly but not perfectly uniform. Tiny density fluctuations, imprinted during inflation and visible today in the cosmic microwave background, served as the seeds of all future structure. Regions slightly denser than average attracted surrounding matter through gravity, growing denser over time. Regions slightly less dense than average lost matter to their denser neighbors, becoming emptier. Over billions of years, this process amplified the initial fluctuations into the cosmic web we see today. Matter drained out of the underdense regions, flowing along gravitational gradients toward the filaments and nodes. The underdense regions expanded, becoming voids. The voids grew not just because matter left them, but because the cosmic expansion itself preferentially expanded the lower density regions, which had less gravitational self-attraction to resist the expansion. This process is well reproduced by computer simulations of cosmic structure formation, the Millennium Simulation, the Illustris Simulation, and more recently the Illustristing and Flamingo simulations have modeled the gravitational evolution of billions of particles representing dark matter and gas. Starting from initial conditions matched to the cosmic microwave background, these simulations produce cosmic webs that closely match the observed distribution of galaxies, including the sizes and emptiness of voids. The largest known structures in the universe are filaments and walls of galaxies that stretch billions of light years. The Hercules Corona Borealis Great Wall, identified in 2013 through the distribution of gamma-ray bursts, appears to span approximately 10 billion light years. If confirmed as a single coherent structure, it would challenge the cosmological principle, the assumption that on sufficiently large scales the universe is homogeneous and isotropic, meaning the same everywhere and in every direction. The scale at which homogeneity should emerge is thought to be a few 100 million light-years. A structure 10 billion light-years long would exceed that scale dramatically. Whether the Hercules Corona Borealis Great Wall is truly a single connected structure or a chance alignment of smaller structures remains debated. The same question applies to other enormous structures identified in galaxy surveys, such as the giant GRB ring and the huge, large quasar group. These discoveries push the boundaries of our models and may require revisions to our understanding of how structure formed in the early universe. Our own position in the cosmic web is becoming clearer. In 2014, a team led by R. Brent Tully published a paper defining a new supercluster that they named Laniakea, a Hawaiian word meaning immense heaven, by mapping the peculiar velocities of thousands of galaxies, the motions they have over and above the general expansion of the universe. Tully and his colleagues identified a basin of gravitational attraction encompassing roughly 100,000 galaxies across a region about 520 million light-years in diameter. All of these galaxies, including the Milky Way, are flowing toward a gravitational center located in the direction of the constellations Centaurus and Norma. This region, known since the 1970s as the Great Attractor, had long puzzled astronomers because it lies behind the plane of the Milky Way, in a zone of the sky obscured by the dust and stars of our own galaxy. Observations in infrared and X-ray wavelengths, which penetrate dust better than visible light, eventually revealed that the Great Attractor corresponds to a massive concentration of galaxy clusters, including the Norma cluster. But the Great Attractor is not the final destination. More recent work has identified an even larger structure behind it, the Shapley supercluster, a dense concentration of galaxy clusters located roughly 650 million light-years away. The gravitational pull of the Shapley supercluster contributes significantly to the bulk flow of galaxies in our region of the universe. The cosmic web is not static. It is in motion, with rivers of galaxies flowing along filaments toward the densest nodes. Understanding how we measure these distances is itself a story that spans centuries of scientific effort. The cosmic distance ladder is a series of techniques, each calibrated against the one below it, that allows astronomers to measure distances from the nearest stars to the most remote galaxies. The first rung of the ladder is parallax. As the Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars, just as holding your thumb at arm's length and alternately closing each eye makes your thumb appear to jump against the background. The amount of apparent shift, the parallax angle, is inversely proportional to the star's distance. This technique works well for stars within a few hundred light-years, where the parallax angle is large enough to measure. The European Space Agency's Gaia spacecraft, launched in 2013, has measured the parallax of nearly 2 billion stars with unprecedented precision, providing a three-dimensional map of the Milky Way's stellar distribution beyond the range of parallax. Astronomers use standard candles, objects whose intrinsic brightness is known, by comparing the known brightness with the observed brightness. The distance can be calculated because brightness decreases with the square of the distance. The most important standard candles include Cepheid variable stars, whose pulsation period is directly related to their intrinsic luminosity, a relationship discovered by Henrietta Swan Leavitt in 1912, and type Ia supernova thermonuclear explosions of white dwarf stars that reach a remarkably consistent peak luminosity. Cepheid variables can be detected in galaxies up to about 100 million light-years away using the Hubble Space Telescope and the James Webb Space Telescope. Type Ia supernova are brighter and can be detected at cosmological distances of billions of light-years. It was measurements of type Ia supernova in distant galaxies in 1998, a discovery that earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011 at the greatest distances. The expansion of the universe itself becomes the primary distance indicator. The light from distant galaxies is stretched to longer wavelengths by the expansion of space, a phenomenon called cosmological redshift. The amount of redshift is related to the distance and to the time the light has been traveling. The relationship between redshift and distance depends on the expansion history of the universe, which in turn depends on the densities of matter, dark matter, and dark energy. By measuring the redshift of a galaxy's spectral lines, astronomers can determine how far away it is and how long ago the light was emitted. The most distant galaxies observed by the James Webb Space Telescope have redshifts above 13, meaning their light has been traveling for more than 13.4 billion years. These galaxies emitted their light when the universe was less than 400 million years old. What we see is not what those galaxies look like now. They have had over 13 billion years of evolution since the light we detect was emitted. They may have merged with other galaxies, grown enormously, been disrupted, or changed beyond recognition. We are looking at their infant photographs. The observable universe has a radius of approximately 56.5 billion light-years. This number is larger than 13.8 billion light-years, the age of the universe multiplied by the speed of light, because the universe has been expanding the entire time the light was traveling. The galaxies that emitted the most ancient light we detect were much closer when they emitted it, but have since been carried away by the expansion of space. The current distance to them is much greater than the distance the light traveled. This means the observable universe is a sphere, approximately 93 billion light-years in diameter. It contains an estimated 200 billion to 2 trillion galaxies, though the lower end of that range is favored by more recent analyses using deep field surveys. Each galaxy contains billions to trillions of stars. The total number of stars in the observable universe is estimated at roughly 200 billion trillion, or 2 followed by 23 zeros, and the observable universe is almost certainly not the entire universe. It is simply the region from which light has had time to reach us since the Big Bang. The universe may extend far beyond the observable horizon, perhaps infinitely. If the universe is spatially flat, as measurements of the cosmic microwave background strongly suggest, then it extends without boundary. There is no edge. There is no wall. There is simply more universe, beyond the reach of any signal that could ever travel at the speed of light in the finite time since the beginning of the expansion. Expansion of the universe is not like an explosion, expanding into pre-existing space. There is no center of the expansion, and no edge expanding outward. Space itself is expanding uniformly. Every point in the universe sees every other sufficiently distant point receding. The further apart two points are, the faster they recede from each other. This relationship, known as Hubble's law, relates the recession velocity of a galaxy to its distance through a proportionality constant called the Hubble constant. The current best measurements of the Hubble constant produce a value of approximately 67 to 74 kilometers per second per megaparsec, depending on the method used. A megaparsec is about 3.26 million light-years. The discrepancy between measurements is one of the most significant open problems in modern cosmology, known as the Hubble tension. Measurements based on the cosmic microwave background, processed through the standard cosmological model, yield a Hubble constant of about 67.4 kilometers per second per minute. Measurements based on the local cosmic distance ladder, using Kifid variables and type Ia supernova, yield about 73 kilometers per second per megaparsec. The difference, roughly 8%, is statistically significant and has persisted despite years of improved observations and cross-checks. If the discrepancy is real and not the result of some systematic error in the measurements, it implies that the expansion of the universe is not behaving exactly as the standard model predicts. This could point to new physics, perhaps a form of dark energy that changes over time, or an additional component of radiation or particles in the early universe not accounted for in current models. The resolution of the Hubble tension may reshape our understanding of cosmic expansion and, by extension, the distances and fates of the most remote structures in the universe. The expansion is accelerating. This was the unexpected discovery of 1998 that introduced dark energy to cosmology. When astronomers measured the brightness of Type Ia supernova in distant galaxies and compared it to their redshifts, they found that the supernova were dimmer than expected, meaning the galaxies were further away than the simplest models predicted. The universe was not just expanding, but expanding faster and faster over time. The cause of this acceleration is attributed to dark energy, a form of energy that permeates all of space and exerts a negative pressure that drives expansion. In the simplest model, dark energy is a cosmological constant, a fixed energy density of space itself that does not change with time. This is the same cosmological constant that Einstein introduced in his equations of general relativity in 1917 and later called his greatest blunder, though for different reasons than its current application. Dark energy constitutes approximately 68% of the total energy content of the universe. Dark matter, an invisible form of matter that interacts gravitationally but not electromagnetically, constitutes approximately 27%. Ordinary matter, the atoms and molecules that make up stars, planets, and people, constitutes roughly 5%. The dominant component of the universe, the component that determines its ultimate fate, is something we have never directly detected and do not understand. The accelerating expansion has a profound consequence for the far future. Galaxies beyond the local group are receding from us. As the expansion accelerates, the rate of recession increases. Eventually, for any galaxy beyond our gravitational neighborhood, the recession velocity will exceed the speed of light. This does not violate the principles of relativity because the galaxies are not moving through space faster than light. The space between us and them is expanding at a rate that accumulates to a superluminal recession speed over sufficiently large distances. When a galaxy's recession velocity exceeds the speed of light, photons emitted by that galaxy will never reach us. They are carried away by the expanding space faster than they can travel toward us. That galaxy has crossed our cosmological event horizon. It is forever causally disconnected from us. No signal, no matter how energetic, could ever bridge the gap. This is already happening. Most galaxies in the observable universe are currently receding from us faster than light. We can still see them because the light we observe was emitted long ago when they were closer and receding more slowly. But the photons being emitted by those galaxies right now, at this moment, will never reach the Earth. Over cosmic timescales, the observable universe will shrink. Galaxies that are currently visible will gradually redshift out of detectability. Their light will stretch to longer and longer wavelengths, becoming dimmer and dimmer until they fade below the detection threshold of any conceivable instrument. In roughly 100 billion years, all galaxies beyond the local group will have faded beyond observation. A civilization arising at that epoch would survey the sky and find only a single galaxy, the merged remnant of the Milky Way and Andromeda and their satellites. surrounded by apparently empty space in every direction. The cosmic microwave background, which currently provides evidence of the Big Bang, would be redshifted to wavelengths so long that it would be undetectable. There would be no observational evidence that the universe ever contained other galaxies or that it began in a hot, dense state. The history of the cosmos would be invisible. That civilization would not be wrong in its observations. The data would simply not contain enough information to reconstruct the truth. The expansion of the universe would have erased the evidence. This is a humbling realization. We happen to live at a time when the universe is old enough for structure to have formed and galaxies to be visible, but young enough that we can still see them. In cosmic terms, this is a window that will eventually close, the speed of light, which determines the boundary of the observable universe and the pace at which we receive information about distant events, is not a technological limitation. It is a physical law. It emerges from the structure of space-time as described by Einstein's special relativity. Published in 1905, the speed of light in a vacuum is exactly 299,792,458 meters per second. This is not an approximate value. It is exact because the meter is defined in terms of the speed of light. What this means physically is that light always travels at this speed, regardless of the motion of the source or the observer. If you move toward a beam of light, it does not appear to approach you faster. If you move away, it does not appear to recede more slowly. The speed of light is invariant. This invariance has consequences that are directly relevant to cosmic distances. No object with mass can reach the speed of light. As an object accelerates, its kinetic energy increases. But as it approaches the speed of light, the energy required for each additional increment of speed grows without bound. To accelerate a single kilogram to the speed of light would require infinite energy. This is not an engineering problem. It is a mathematical consequence of the geometry of space-time. The fastest macroscopic objects humans have ever produced are still vanishingly slow compared to light. The Parker Solar Probe, which orbits close to the Sun and uses the Sun's gravity to accelerate, has reached speeds of approximately 692,000 kilometers per hour, roughly 0.064% of the speed of light. At that speed, reaching the nearest star would take roughly 6,500 years. Proposed interstellar mission concepts illustrate both the ambition and the constraints. The Breakthrough Starshot Initiative, announced in 2016, proposes using a ground-based laser array to accelerate tiny light sail probes to 20% of the speed of light. At that speed, a probe would reach Alpha Centauri in approximately 20 years, plus the 4-year return time for the signal to travel back to Earth at light speed. But the probes would be only a few grams in mass, carry minimal instruments, and have no ability to decelerate. They would fly through the Alpha Centauri system in a fraction of a second, gathering whatever data they could in that fleeting pass. Even this ambitious concept, which would require engineering breakthroughs that do not yet exist, offers only the briefest glimpse of the nearest star system. For human travel, the constraints are even more severe. A crewed starship would need to carry life support systems, shielding food and fuel for acceleration and deceleration. The mass budget would be enormous. even at 10% of the speed of light, which is far beyond any propulsion system that exists or is plausibly near-term. The journey to Proxima Centauri would take over 40 years, an entire human lifetime spent in transit for a one-way trip to the nearest star. These realities cast the Fermi paradox, the question of why we have not detected signs of extraterrestrial intelligence despite the vastness and age of the universe, in a different light. The universe may be full of life. There may be civilizations on planets orbiting stars thousands of light years away, but the distances between them are so vast, and the speed of light so absolute, that they may never detect each other. Communication at interstellar distances requires waiting years, decades, or millennia for a reply. Interstellar travel, if it is possible at all, would be a generational endeavor measured in centuries. The silence of the cosmos may not indicate absence. It may indicate isolation. Each civilization, if they exist, may be a flickering light in a volume of darkness, so immense that no message could cross it in time to matter. The cosmic microwave background is the oldest light in the universe. It was emitted roughly 380,000 years after the Big Bang, at the moment when the universe cooled enough for neutral hydrogen atoms to form. Before that epoch, the universe was a plasma of charged particles, protons and electrons, through which photons could not travel freely. They were constantly scattered by the charged particles, making the universe opaque, like being inside a dense fog when the temperature dropped to approximately 3000 Kelvin. Electrons and protons combined to form neutral hydrogen atoms, a process called recombination. Neutral hydrogen does not scatter photons efficiently. The universe became transparent, and the photons that were in transit at that moment have been traveling freely ever since. Those photons have been stretched by the expansion of the universe from their original temperature of 3000 Kelvin to their current temperature of approximately 2.725 Kelvin, deep in the microwave region of the electromagnetic spectrum. The cosmic microwave background is remarkably uniform. Its temperature is the same in every direction to within 1 part in 100,000. This uniformity is itself a puzzle, because regions of the sky separated by more than about 1 degree, corresponding to regions that were never in causal contact in the standard Big Bang model, should have had no way to reach the same temperature. The solution is cosmic inflation, a period of exponentially rapid expansion in the first fraction of a second after the Big Bang, which stretched a tiny, causally connected region to a size larger than the entire observable universe, ensuring uniformity. The tiny variations in the cosmic microwave background, the 1 part in 100,000 fluctuations, are the seeds of all cosmic structure. The slightly denser regions in the infant universe attracted more matter through gravity, growing over billions of years into the galaxies, clusters, filaments, and voids that we observe today. The slightly less dense regions became the voids. The pattern of fluctuations in the cosmic microwave background encodes information about the composition, geometry, and age of the universe with extraordinary precision. Measurements by the Cosmic Background Explorer satellite in the early 1990s first detected the fluctuations. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped them with much higher resolution. The Planck satellite, operated by the European Space Agency from 2009 to 2013 produced the definitive map of the cosmic microwave background, measuring the fluctuations to a precision that allows the determination of cosmological parameters to within fractions of a percent dot from the Planck data. We know that the universe is 13.8 billion years old, that it is spatially flat to within the precision of measurement, that ordinary matter constitutes 4.9% of the total energy content, that dark matter constitutes 26.8%, and that dark energy constitutes 68.3%. These numbers define the universe we live in, and they are all extracted from the faint microwave glow left over from the first moments of cosmic transparency. The cosmic microwave background is also a wall. It is the most distant thing we can observe. Beyond it, the universe was opaque. No light from before recombination can reach us directly. What lies on the other side of that wall? The universe, in its first 380,000 years, can only be probed indirectly through its gravitational effects on the cosmic microwave background, through the abundances of light elements produced in the first few minutes, or through gravitational waves generated in the earliest instants. Gravitational waves offer a way to see further back than any electromagnetic observation. These are ripples in the fabric of space-time produced by accelerating masses, predicted by Einstein in 1916 and first directly detected by the Laser Interferometer Gravitational Wave Observatory in 2015. The detected signal came from the merger of two stellar mass black holes, approximately 1.3 billion light-years away. Since then, over 100 gravitational wave events have been detected, including mergers of black holes, mergers of neutron stars, and mixed mergers of one of each. Gravitational waves from the early universe, if detected, could provide information about conditions in the first fraction of a second, long before the cosmic microwave background was emitted. Inflation, the rapid expansion of the universe in its earliest moments, is predicted to have generated a background of gravitational waves that would be imprinted on the polarization of the cosmic microwave background. Detecting this signature is one of the primary goals of current and next-generation cosmic microwave background experiments, including the Simons Observatory and the proposed CMBs for Project. Beyond the observable universe lies territory that is fundamentally inaccessible to observation but not to theory. If the standard model of cosmology is correct, the universe extends beyond our observable horizon with the same physical laws and the same types of structures. There is no reason to expect a boundary or an edge. Space simply continues. Some cosmological models suggest that the universe may be much larger than the observable portion, perhaps by factors of hundreds or thousands or more. Others, based on the theory of eternal inflation, suggest that our observable universe is one of many bubble universes in a vastly larger multiverse, each potentially with different physical constants and different laws of physics. In this scenario, the distances between bubble universes are not just immense, but conceptually different from distances within our universe. They are separated by regions of inflating space that expand faster than any signal could cross. Whether the multiverse exists is not currently a testable scientific question, though theorists continue to explore whether any observable signatures of other bubble universes could be imprinted on the cosmic microwave background or on the large-scale structure of our universe. None have been found. What is testable and what is being actively tested is the detailed structure and evolution of the observable universe. The next generation of surveys and telescopes will push our understanding of cosmic distances and structures to new precision. The Euclid Space Telescope, launched in 2023, is designed to map the shapes and redshifts of billions of galaxies across 10 billion light-years of cosmic history. Its primary goal is to measure the effects of dark energy on the expansion of the universe and on the growth of cosmic structure with unprecedented precision. The Vera C. Rubin Observatory, located in Chile and currently beginning science operations, will survey the entire visible sky every few nights with a camera containing 3.2 billion pixels. Over its 10-year primary survey, it will detect and catalog roughly 20 billion galaxies and a comparable number of stars, producing the most comprehensive map of the universe ever assembled. The Nancy Grace Roman Space Telescope, expected to launch in the mid-2020s, will combine a wide field of view with the resolution of the Hubble Space Telescope, allowing deep surveys of large areas of sky. It will measure cosmic distances using multiple techniques simultaneously, providing cross-checks that could help resolve the Hubble tension. The Square Kilometre Array, a radio telescope being built in Australia and South Africa, will observe the universe in radio wavelengths with sensitivity and resolution far beyond any existing radio telescope. Among its goals is detecting the 21-centimeter emission line of neutral hydrogen from the period before the first stars formed, the so-called cosmic Dark Ages, a period that has never been directly observed. These instruments will not merely refine existing knowledge. They will access regimes of distance and time that have never been probed, potentially revealing new structures, new physics, and new constraints on the models that describe the universe. The distances in space are not abstractions. They have physical consequences. They determine what we can observe, what we can reach, what we can communicate with, and what is forever beyond our influence. They shape the past history and the future fate of everything that exists. The universe is roughly 13.8 billion years old. In that time, light has traveled a fixed distance. That distance defines the boundary of the knowable. Beyond it, physics continues, but knowledge stops. The observable universe is not all there is. It is all there is for us. Every measurement of a distant galaxy is an act of looking backward in time. The light from a galaxy 1 billion light-years away left that galaxy 1 billion years ago. The galaxy we see is not the galaxy that exists now. It is a memory. The real galaxy, the galaxy as it is at this moment, is unknowable until its current light reaches us 1 billion years from now. And by then, we will have moved, the galaxy will have moved, and the universe will have expanded further at the largest scales. The universe is a place where everything is receding from everything else, where most of the volume contains essentially nothing, where the distances between the interesting parts are so vast that crossing them would outlast civilizations. The cosmic web of filaments and voids, the superclusters and walls, the expanding horizon beyond which galaxies vanish forever. These are not metaphors for isolation. They are the structure of reality, and within that reality, on a small rocky planet orbiting an average star in a minor spiral arm of an unremarkable galaxy. A species recently evolved enough to ask questions has built instruments precise enough to measure the expansion of space, detect gravitational waves from merging black holes a billion light-years away, and map the temperature fluctuations of radiation emitted. When the universe was 380,000 years old, the distances are vast. The isolation is real, but the ability to comprehend and measure that isolation, to take the raw data of redshifts and parallax angles and brightness curves and convert them into a coherent picture of the universe across 13.8 billion years of history, that is worth knowing about. If following these developments as new data arrives from the James Webb Space Telescope, the Euclid mission, and the Vera Rubin Observatory sounds worthwhile subscribing, make sure you see those results when they come. No effort required on your part. We have measured the distances. We have mapped the voids. We have identified the structures that stretch across billions of light years. And with every new measurement, the universe turns out to be larger, emptier, and more precisely structured than the one before. The question that remains is not whether the distances are real. They are. The question is whether there is anyone else out there measuring them too, from a different point in the web, looking out across the same incomprehensible emptiness, and wondering the same thing. There is another dimension to cosmic distance that deserves attention, and it concerns not just space, but time. The two are inseparable in the framework of general relativity. The distances between galaxies are not fixed. They change with the expansion of the universe. A galaxy that was 1 billion light-years away when its light was emitted may now be several billion light-years away because the space between us and it expanded during the billions of years the light was in transit. Conversely, the most distant galaxies we observe were much closer when they emitted the light we see. The universe has been expanding the entire time, stretching both the distances and the wavelengths of the photons traveling through it. This interplay of distance and time creates what cosmologists call the look-back time. When we observe a galaxy at a redshift of 1, the light has been traveling for approximately 7.7 billion years. The galaxy we see is 7.7 billion years younger than it is today. At a redshift of 2, the look-back time is approximately 10.3 billion years. At a redshift of 10, it is roughly 13.2 billion years, corresponding to a universe less than 500 million years old. The James Webb Space Telescope has detected galaxies at redshifts above 14, showing the universe as it was within the first 300 million years of its existence. Some of these galaxies are unexpectedly bright and massive for their age, suggesting that galaxy formation began earlier and proceeded faster than standard models predicted. This has generated significant scientific discussion about whether the models of early galaxy formation need revision, whether the stellar populations in these early galaxies were fundamentally different from those in nearby galaxies, or whether unknown processes accelerated their growth. These early galaxies are not just distant in space, they are distant in time. They represent a universe that was fundamentally different from the one we inhabit. The first stars had not yet enriched the interstellar medium with heavy elements. The galaxies were smaller, more chaotic, and undergoing rapid bursts of star formation. the intergalactic medium was still largely neutral hydrogen, not yet ionized by the ultraviolet radiation from the first generations of stars and quasars. The process by which the universe transitioned from this neutral state to the ionized state we observe today, called the Epoch of Reionization, is one of the major chapters in cosmic history that the James Webb Space Telescope was designed to investigate. The relationship between distance and time also means that different distances correspond to different physical conditions. Looking at nearby galaxies shows us the universe as it is now. Looking at galaxies a few billion light-years away shows us the universe when star formation was at its peak, roughly 10 billion years ago. Looking at the most distant galaxies shows us the universe in its infancy, and looking at the cosmic microwave background shows us the universe at the moment it became transparent, 380,000 years after the Big Bang. In this sense, every telescope is a time machine, and the distances it measures are not just spatial separations, but temporal ones, windows into epochs that no longer exist and can never be visited. The concept of deep time is as difficult for the human brain to process as deep space. The age of the universe, 13.8 billion years, is a number that conveys almost no intuitive meaning. To put it in perspective, if the entire history of the universe were compressed into a single calendar year, with the Big Bang occurring at midnight on January 1st and the present moment at midnight on December 30th, the Milky Way would form around March. The Sun and Earth would form in early September. The first multicellular life would appear in mid-November. The dinosaurs would go extinct on December 26th. All of recorded human history, every civilization, every empire, every scientific discovery, would occur in the final second of the final minute of the final hour of December 31st. Every galaxy we see in the sky has a history measured in billions of years. The light from some of them has been traveling since before the Earth existed. When we observe a galaxy 10 billion light-years away, the photons entering our telescopes left their source when the Sun had not yet formed, when the atoms that would eventually become the Earth were still scattered through interstellar space as gas and dust in a previous generation of stars. The physical mechanism governing cosmic distances are themselves evolving. The expansion rate of the universe has not been constant. In the first few billion years after the Big Bang, the expansion was decelerating. The mutual gravitational attraction of all the matter and radiation in the universe was slowing the expansion down. If this deceleration had continued, the expansion might have eventually halted and reversed, leading to a contraction and a big crunch. Instead, approximately 5 to 6 billion years ago, the deceleration turned into acceleration. Dark energy, whatever it is, became the dominant component of the universe's energy budget. The expansion began to speed up rather than slow down. This transition from deceleration to acceleration is one of the most important events in cosmic history because it determined the ultimate fate of the universe. If the acceleration continues at its current rate, the universe will expand forever. Galaxies will recede beyond the observable horizon. Stars will exhaust their nuclear fuel. The last red dwarfs, which burn their hydrogen slowly and can shine for trillions of years, will eventually go dark. The universe will enter an era of degenerate remnants, white dwarfs, neutron stars, and black holes slowly cooling in an expanding void. Black holes themselves will eventually evaporate through Hawking radiation on timescales so long that they exceed 10 to the 67th years for stellar mass black holes and much longer for supermassive ones. After all, the black holes evaporate. The universe will contain nothing but a thin, cooling gas of photons, neutrinos, and perhaps the occasional positronium atom dispersed across a volume so large and so empty that no structure of any kind can form. This is the heat death of the universe, the endpoint predicted by the second law of thermodynamics applied to cosmology. It is not a dramatic conclusion. It is a gradual fading, an asymptotic approach to a state of maximum entropy in which nothing happens because nothing can happen. The distances between the few remaining particles will be so great and the energy available so small that no interaction will occur for timescales that dwarf the current age of the universe by factors beyond comprehension. Whether this fate is truly inevitable depends on the nature of dark energy. If dark energy is truly a cosmological constant, unchanging with time, the heat death is the outcome. If dark energy changes over time, the fate could be different. If dark energy strengthens, a scenario called the Big Rip, the expansion could eventually become so violent that it tears apart galaxies, then solar systems, then planets, then atoms themselves, ending the universe in a cataclysmic expansion at a finite time in the future. If dark energy weakens or reverses, the universe could eventually Current data are consistent with a cosmological constant, but do not rule out slow changes in dark energy. Resolving this question is one of the primary goals of the Euclid, Rubin, and Roman missions. There is also the question of what the large-scale geometry of the universe tells us about its total size. The observable universe appears spatially flat, meaning that parallel lines remain parallel over cosmic distances, and the angles of large triangles sum to 180 degrees. Spatial flatness, combined with the standard model of cosmology, implies that the total universe may be much larger than the observable portion. Some estimates, based on the precision of the flatness measurement, suggest the total universe could be at least 250 times larger in radius than the observable universe. Others suggest it could be infinite. An infinite universe has a disorienting implication. In an infinite universe, with a finite number of possible quantum states for any given volume of space, every possible configuration of matter must be repeated somewhere. There would be exact copies of every person, every planet, every galaxy, scattered across an infinite expanse. These copies would be separated by distances so enormous that no number currently in use can express them in any meaningful units. The distance to the nearest exact copy of the observable universe. If the universe is truly infinite and the matter distribution is ergodic, has been estimated at approximately 10 to the 10 to the 122 meters, a number whose exponent alone is far larger than the number of particles in the observable universe. Whether such copies actually exist depends on assumptions about the nature of infinity and the distribution of quantum states that are far from settled. The idea remains a mathematical consequence of certain cosmological models rather than an observational result. But it illustrates how the concept of distance, pushed to its extreme, leads to conclusions that strain the boundaries of what human thought can accommodate. It is a constraint on knowledge, a barrier to contact, a clock measuring the age of photons, and a sentence determining the fate of structures. The distances between galaxies dictate whether civilizations could ever communicate. The distances between galaxy clusters determine how the cosmic web evolves. The distance to the cosmic microwave background defines the limit of electromagnetic observation. The distance to the cosmological event horizon defines the limit of causal influence. Every attempt to understand the universe begins and ends with distance. How far away is it? How long has the light been traveling? How much has the space expanded since the light was emitted? These questions are not preliminary. They are the substance of cosmology itself. The instruments being deployed now and in the coming decades will measure these distances with a precision that would have been inconceivable to the astronomers who first realized that the faint nebulae they observed through their telescopes were entire galaxies millions of light years away. Edwin Hubble established this fact in 1924, less than a century ago. In the span of a single human lifetime, we have gone from not knowing that other galaxies existed, mapping billions of them across 13 billion years of cosmic history. The rate of discovery is accelerating even as the universe itself accelerates away from us. Each new survey reveals structures larger than the last, voids emptier than expected, and distances that stretch the limits of instrumentation and imagination. The cosmic web grows more detailed with every observation. The story of the universe unfolds backward through time with every exciton detected from the deep field. We are a species that can measure the curvature of space-time, detect the wobble of a star caused by an orbiting planet for light years away, and extract the composition of the universe from the faint microwave glow of the Big Bang. We do all of this from a single point in a cosmic web that extends billions of light years in every direction, surrounded by voids containing essentially nothing, on a planet orbiting a star that would be invisible from even the nearest neighboring galaxy. The universe is mostly empty. The distances between the things that fill it are mostly uncrossable. The information we can gather about it is limited by the speed of light and the age of the cosmos. And yet, what we have gathered in the brief window of cosmic time during which our species has existed and our instruments have operated is a remarkably complete and detailed picture of where we are, how far everything else is, and what lies between. That picture is still being refined. The next decade of observations will test whether dark energy is truly constant, whether the Hubble tension reflects new physics, whether the earliest galaxies formed through known mechanisms, and whether the large-scale structure of the universe conforms to or violates the cosmological principle at the largest scales. The distances will not shrink. If anything, they will grow as the expansion continues and the observable universe slowly contracts. But our ability to measure them, to understand what they mean, and to situate ourselves within the immense, mostly empty, quietly expanding structure of the cosmos continues to improve. That is the real story of cosmic distance. Not that it is big, though it is. Not that it is frightening, though it can be, but that it is measurable. That the voids and filaments and horizons and walls of ancient radiation can be mapped, characterized, and understood by a civilization that has existed for an eye blink of cosmic time, on a world so small that it would be invisible from even a modest cosmic distance. The distances are real, the emptiness is real, and the fact that we can comprehend both is, by any measure, extraordinary. To deepen the appreciation for what these distances mean physically, consider what would happen if you attempted to communicate across them. Electromagnetic signals, radio waves, laser pulses, any form of light, travel at 300,000 kilometers per second. A message sent to the nearest star system, Alpha Centauri, would arrive in approximately 4 years and 3 months. A reply would take the same time. A single exchange of information would require nearly 9 years. A conversation at that pace would be so slow that the participants might die before it concluded. Roughly 54 million light-years. A message sent today would arrive 54 million years from now. The recipient civilization would be receiving information from an era so remote, by the time a reply arrived back at Earth, 108 million years would have passed. The continents would have shifted, species would have evolved and gone extinct. The civilization that sent the message would be unrecognizable or long gone at the distance of the cosmic microwave background. Communication is not merely slow, it is impossible. The regions of the universe that emitted that radiation are now approximately 46 billion light-years away. No signal sent from Earth could ever reach them because the space between us is expanding faster than light can cross it. They are beyond our cosmological event horizon, permanently isolated from us by the geometry of expanding space-time. This isolation is not a failure of technology. It is a feature of the universe. The speed of light is not an engineering limit to be overcome with better engines or more energy. It is a structural property of space-time itself. Breaking the light-speed barrier is not like breaking the sound barrier. Sound travels through air, and supersonic flight simply outpaces the pressure waves. Light speed is not a wave in a medium. It is the maximum rate at which cause can propagate to effect in the fabric of reality. Exceeding it would mean effects occurring before their causes, which would break the logical structure of physics. Some speculative proposals exist for circumventing the light speed limit without technically violating it. The Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994, describes a configuration of space-time in which a bubble of flat space moves through the universe faster than light, while the contents of the bubble remain stationary relative to the flat space inside. The idea exploits the fact that general relativity places no limit on how fast space itself can expand or contract, only on how fast objects can move through space. The Alcubierre drive is mathematically consistent with general relativity. A space-time metric describing the required bubble can be written down and is a valid solution of Einstein's field equations. But the energy requirements are extraordinary. The original formulation required negative energy densities, which violate the classical energy conditions and are only known to occur in certain quantum effects, like the Casimir effect, at magnitudes far too small to be useful. Subsequent refinements have reduced the energy requirements but not eliminated the fundamental problems. Creating the required space-time geometry appears to demand forms of matter energy that may not exist, and the stability of the bubble, the problem of creating or stopping it. and the question of what happens to the contents when it decelerates are all unresolved. As of now, the Alcubierre drive is a theoretical curiosity rather than a pathway to interstellar travel. It demonstrates that general relativity does not forbid faster-than-light travel in principle, but does not provide a practical mechanism for achieving it. The distances remain another approach to spanning cosmic distances, at least conceptually, involves wormholes, tunnels through space-time connecting distant points. Wormholes are permitted by general relativity. The Einstein-Rosen bridge, described by Albert Einstein and Nathan Rosen in 19. However, classical wormholes are unstable. They collapse faster than anything could traverse them. Keeping a wormhole open long enough to pass through would require exotic matter with negative energy density, the same problematic requirement that plagues the Alcubierre drive. No wormhole has ever been observed. No mechanism for creating one is known. And even if stable, traversable wormholes could be created, the question of where they connect and whether their endpoints could be controlled is entirely unknown. They remain mathematical possibilities rather than physical realities. The hard truth is that with current and foreseeable physics, the distances in space are barriers that cannot be overcome. They can be measured, mapped, and understood, but they cannot be crossed on timescales relevant to human civilization. This has profound implications for the search for extraterrestrial intelligence. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in the Milky Way by multiplying together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets suitable for life, the fraction that develop life, the fraction that develop intelligence, the fraction that develop technology, and the average lifetime of a technological civilization. The values of most of these factors are uncertain by orders of magnitude. Estimates of the number of communicative civilizations in the galaxy range from fewer than one, meaning we are alone, to millions. But even the optimistic estimates do not eliminate the distance problem. If 1 million civilizations existed in the Milky Way, the average distance between them would still be roughly 1,000 light-years. Communication would take millennia. Detection would require extraordinary sensitivity or extraordinary luck. The search for extraterrestrial intelligence, known by the abbreviation SETI, has been listening for radio signals from other civilizations since 1960. The most systematic survey, Project Phoenix, operated from 1995 to 2004 and examined approximately 800 nearby sun-like stars for narrowband radio signals. No confirmed detection was made. The Breakthrough Listen initiative, launched in 2015 with $100 million in funding, is the most comprehensive SETI program ever undertaken, surveying over 1 million nearby stars, the entire galactic plane, and 100 nearby galaxies. As of the current date, no confirmed signal of extraterrestrial origin has been detected. The absence of a detection does not prove absence of life. The parameter space to search is enormous. An alien civilization might communicate at frequencies we are not monitoring, or using modulation schemes our algorithms do not recognize, or in a direction we are not observing. They might use tightly focused laser beams rather than omnidirectional radio broadcasts. They might have been broadcasting for millions of years, but stopped before their signals reached us. Or they might be so far away that their signals are too faint to detect with current. Technology. The distances impose another constraint on SETI. Radio signals spread out as they travel, growing weaker with the square of the distance. A television broadcast leaking from Earth, which is a common example used to illustrate the idea of detectable human signals, would be undetectable by any existing telescope at the distance of even the nearest star. Only deliberately targeted, high-power transmissions could be detected at interstellar distances, and detecting them requires knowing where and when to look. The galaxy might be full of life, full of technology, full of civilizations that have built wonders we cannot imagine, and we might never know, because the distances between us and them are so great that their signals never arrive, or arrive so weakened by distance that they are indistinguishable from noise. This brings us back to the structure of the universe itself, and the question of whether the cosmic web has any bearing on the distribution of life. Galaxies in dense cluster environments have different properties than galaxies in voids. Cluster galaxies tend to be older, redder, and gasper. Their star formation quenched by environmental effects like ram pressure stripping, in which the hot gas between galaxies in a cluster blows away the cold gas needed for star formation. Void galaxies, by contrast, tend to be bluer and more actively forming stars, but they have fewer opportunities for enrichment through galactic interactions and mergers. If life requires heavy elements, which are produced in stars and distributed by supernova, then the chemical evolution of a galaxy affects the probability of life arising within it. Galaxies in denser environments may have been enriched earlier, potentially allowing life to arise sooner. Galaxies in voids may have lower metallicity, the astronomical term for the abundance of elements heavier than helium, which could delay or reduce the frequency of rocky planet formation. The habitable zone concept, usually applied to the distance of a planet from its star, can be extended to galactic scales. The galactic habitable zone is the region of a galaxy where conditions are favorable for life, far enough from the galactic center to avoid intense radiation from the supermassive black hole and from the high density of supernova, but close enough to benefit from the heavy element enrichment produced by previous generations of stars. The Sun sits roughly in the middle of the Milky Way's estimated galactic habitable zone. Whether the galactic habitable zone is a meaningful concept or an oversimplification is debated. The Milky Way's habitability depends on many factors beyond metallicity and radiation levels, including the frequency of nearby supernova and gamma-ray bursts, the stability of planetary orbits in the galactic tidal field, and the rate of cometary bombardment from the Oort cloud, which itself may be perturbed by passing stars at the cosmic web level. The question becomes even more speculative. Are voids habitable? Could a civilization arise in a void galaxy, isolated not just by stellar distances but by intergalactic distances measured in millions of light years to the nearest neighbor? Such a civilization would look out at a sky far emptier than ours, with far fewer visible galaxies, and might conclude that the universe is a far lonelier place than we believe it to be. The structure of the cosmic web also has implications for the far future of any civilization that manages to persist. If a civilization survives for billions of years, it will face the gradual disappearance of the external universe as the expansion carries galaxies beyond the observable horizon. The local group, gravitationally bound, will persist as a single merged galaxy, but everything beyond it will recede and fade. A sufficiently advanced civilization might attempt to preserve information about the wider universe before it becomes unobservable. They might record the positions and properties of galaxies that will eventually disappear, maintaining a cosmological archive that future generations could not reconstruct from observation alone. The physicist and cosmologist Lawrence Krauss and Robert Scherer have written about this scenario, arguing that civilizations in the far future will face a fundamentally impoverished observational universe and may not even be able to derive the correct cosmological model from the data available to them. Is the ultimate consequence of cosmic distance combined with cosmic expansion. Not only are the distances vast, they are growing, and as they grow, the universe becomes, from any single observer's perspective, progressively simpler, emptier, and more isolated. The current moment in cosmic history is, in this sense, privileged. We live at a time when the universe is old enough for complexity to have emerged, stars to have formed heavy elements, planets to have coalesced, and life to have evolved, but young enough that the cosmic web is still visible. The cosmic microwave background is still detectable, and the expansion has not yet carried the evidence of the Big Bang beyond reach. Billions of years from now, these conditions will no longer hold. The evidence will have been erased by distance. The cosmic web will have stretched beyond detection. The microwave background will have cooled below any practical measurement threshold. The universe will still exist, but its history will be unreadable. We are right now in the narrow window when the universe can be understood from within. The distances that define it are measurable. The structures that compose it are mapped. The physics that governs it is testable. That window will not last forever, but for now, it is open, and what we can see through it is a universe that is overwhelmingly empty, staggeringly large, precisely structured, and still, despite everything, comprehensible. Consider one more scale of distance that is rarely discussed but deeply illuminating. The distance between atoms within your own body is relative to their size, comparable to the distances between stars. An atom is approximately 1/10,000,000th of a meter across. The nucleus at its center is roughly 100,000 times smaller than the atom itself. If an atom were scaled up to the size of a football stadium, the nucleus would be a grain of rice at the center. The electrons would be somewhere in the stands, and the rest of the volume would be empty space. Matter, at the atomic level, is overwhelmingly empty. The chair you sit on, the floor beneath your feet, the bones in your body. These are not solid in any meaningful physical sense. They are clouds of electrons repelling other clouds of electrons through electromagnetic force, creating the illusion of solidity at the macroscopic scale. The actual particles occupy a negligible fraction of the volume they appear to fill. This means that the emptiness of space is not a distant abstraction. It is present in every object, in every atom, in your own hand. The universe is empty at every scale, from the subatomic to the cosmic. Emptiness is not a property of deep space. It is a property of existence. The distances between planets are emptier than any laboratory vacuum. The distances between stars are emptier than the distances between planets. The distances between galaxies are emptier than the distances between stars. And the voids between galaxy clusters are emptier still. At each level, the fraction of volume occupied by matter decreases. The cosmic web is a structure of matter drawn along thin filaments and nodes, surrounded by voids that fill most of the total volume, and the matter itself, at the atomic scale, is mostly empty. The total amount of ordinary matter in the observable universe, all the atoms in all the stars and planets and gas clouds and dust and living things, would fit in a volume remarkably small compared to the observable universe itself. If you compressed all the ordinary matter in the observable universe to the density of water, 1 kilogram per liter, it would form a sphere roughly 4 light-years in radius. The entire mass of 2 trillion galaxies, condensed into a ball of water, would be smaller than the distance to the nearest star. This calculation excludes dark matter and dark energy, which make up the vast majority of the universe's energy content but are not made of atoms, and do not occupy space in the same way. Including dark matter would increase the sphere's radius, but not dramatically. The universe is, by any accounting, almost entirely empty. And yet, within that emptiness, structure has formed. Gravity, operating over billions of years, has gathered diffuse gas into stars, stars into galaxies, galaxies into clusters, and clusters into the cosmic web. The complexity of the observable universe, all of it, emerged from a nearly uniform initial state through the patient accumulation of gravitational effects across cosmic time. The distances are not obstacles to structure formation. They are the canvas on which structure forms. Without vast distances, there would be no room for the cosmic web to develop. Without billions of years of cosmic time, there would be no opportunity for gravity to do its work. The emptiness and the immensity are not features to be lamented. They are the conditions that make the universe possible. Every filament of the cosmic web, every galaxy cluster at every node, every void stretching hundreds of millions of light-years across, exists because the universe is exactly as large and as old and as empty as it is. A smaller universe, a younger universe, a denser universe would produce a different structure, or no structure at all. The distances that seem so incomprehensible are precisely the distances required for the universe to be what it is. That may be the deepest lesson of cosmic distance. It is not a flaw in the design of the universe. It is the design. The voids are not wasted space. They are the counterpart to the filaments, the negative space that defines the structure. The distances between galaxies are not barriers to be overcome. They are the gravitational playing field on which cosmic evolution unfolds. We measure these distances because they tell us what the universe is, not what it contains, but what it is. The answer, as far as current physics can determine, is a vast, expanding, mostly empty space with a thin tracery of matter arranged in a web-like pattern, governed by gravity and dark energy, evolving slowly toward a state of maximum emptiness and minimum structure. The universe began dense and hot and uniform. It will end sparse and cold and featureless. Between those endpoints lies a brief interval of structure, complexity, and the possibility of understanding. We inhabit that interval. The distances that define it are, for now, within our ability to measure and comprehend. That is neither comforting nor terrifying. It is simply what the measurements show. And the measurements, taken from a small planet orbiting an ordinary star in the quiet suburbs of a galaxy that is itself a minor member of a modest cluster at the edge of a supercluster drifting through the cosmic web, are remarkably, improbably, beautifully precise.